So today I want to talk a little bit more about quaternions and a problem that I found with quaternions. Now the problem isn't with quaternions, the problem is actually with the language surrounding quaternions, okay? And in particular with the symbolic language of algebra. Okay, so there appears to be a problem with the language, and the language has to do with how the symbolic language has been expressed over time. So this is something I've seen over and over and over again. It seems to be kind of a ubiquitous problem with the language and how people are describing what quaternions are. So a few videos back, I brought your attention to this paper, The Evolution from the Complex Plane to the Quaternion Coordinate System to the Transpatial Geometry. So the problem that I'm finding, so in this section here, the section on the complex plane, he makes the following statement. Okay, he says, in the standard classical mechanics 3D Cartesian coordinate system, the notation symbols I, J, and K are used to designate the triply orthogonal unit vector set with the values I equals J equals K equals 1. Okay, so this expression here, I equals J equals K equals 1, does not define a triply orthogonal unit vector. Okay, unit vectors, so 1, okay, the 1 here is a scalar. 1 is the identity of the real numbers. Okay, so saying that making the statement I equals J equals K equals 1 and referring to that as a triply orthogonal unit vector is not quite correct. Okay, so then he goes on to talk about quaternions, and here he is using I, J, and K in this expression. Also, the one thing I do like about this expression is he puts the 1 in there. So he is saying the quaternion, Hamilton's quaternion, is expressed as A times 1 plus B times I plus C times J plus D times K. Okay, so this is the problem with the language where they use letters, I, J, and K. These letters here are not the same as these letters here, but when you use them together in the same paper without clarifying, then one might begin to think that this I, J, and K are the same as this I, J, and K. Okay, so, but with this paper, the main problem is here where I equals J equals K equals 1 does not define triply orthogonal unit vectors. Okay, so here is another paper that does correctly define the triply orthogonal unit vectors. Okay, this is called Quaternions and Rotations by Yan Bin G or J, I'm not sure how to say that. Okay, so in the section, in this paper, in the section on quaternion algebra, he says the set of quaternions together with two operations, addition and multiplication, form a non-commutative ring. Okay, so this is true. The standard orthonormal basis for R3, so real, the Cartesian coordinate system, is given by the 3 unit vectors I equals 1, 0, 0, J equals 0, 1, 0, and K equals 0, 0, 1. Okay, so this is actually the correct way of expressing the 3 orthogonal axes. Okay, but the problem I have with this, and we have the same problem where he's using I, J, and K to define these 3 unit vectors, and which is correct compared to this, the I equals J equals K equals 1 is not the correct way of expressing the orthogonal unit vectors. This is in fact the correct way of writing those 3 vectors. Okay, so then he goes on to say a quaternion Q is defined as the sum of a scalar Q0 and a vector Q equals these 3, so these 3 coordinates here. And then he writes this expression here where he's using I, J, and K. And what is not clear from, and this is all in one statement, so this is not even broken up. This is all in one sentence practically, where he, or two sentences where he introduces I, j, and k as the unit vectors, and then I, j, and k as the quaternion, which he refers to as a vector. Okay, but he's referring to the Q1, Q2, and Q3 as a vector, and then writing this expression and writing I, j, and k. So this might give the reader the false impression that this I, j, and k are the same as this I, j, and k, and that cannot be further from the truth. So to clear this up, what I did was I went to ChatGPT and I asked it a couple of questions. Okay, so I said, that is the difference. Actually, what I meant to say is, what is the difference? I spelled that is the difference, but what is the difference between I, j, and k in vector calculus and I, j, and k in quaternions? Okay, so the labels I, j, and k are used in both vector calculus and quaternion algebra, but they have different meanings and properties in each context. Okay, so let's explore these differences. So in vector calculus, I, j, and k are the unit vectors that define the directions along the x, y, and z axes in three-dimensional space. Okay, so I is the unit vector in the x direction, which was shown in the paper, that paper I showed you. J is the unit vector in the y direction, and k is the unit vector in the z direction. And these are you can think of them as 1/3 matrices. If I were going to implement this as a matrix, it would be a 1/3 matrix. These vectors are orthogonal, perpendicular to each other, and have a magnitude of 1. Okay, so the magnitude of each vector is 1, because if you calculate the distance of this unit vector, it is going to equal 1. Okay, they are used to express any vector in 3D space as a combination of these vectors. The operations involving these vectors are like the cross product, follow the right-hand rule, and have specific results based on their orthogonal nature. Okay, so I times j is equal to k, j times k equals I, and k times I equals j. So that's kind of similar to quaternions in that sense. Okay, so, but their functions are different. The functionality is different. So in quaternions, the quaternion I, j, and k are not unit vectors, but they are imaginary units. Okay, so I agree with that. They're not unit vectors, but they are imaginary units. Quaternions extend complex numbers to 4 dimensions and are used to represent rotations in 3D space. Okay, so the quaternion expressed as q is equal to w plus xi plus yj plus zk, where w, x, and y, and z are real numbers, and I, j, and k are imaginary units. Okay, they are imaginary units. They're just not unit vectors. Okay, so with the following properties that we know, I squared equals j squared equals k squared equals ijk equals -1. Okay, so the properties are non-commutative. So I times j equals k, but j times k equals I, and k times I equals j. But the reverse is the opposite. So j times I equals -k, k times j equals -I, and I times k equals -j. The rules indicate that the order in which you multiply these matters, which is different from commutative nature of multiplication of vectors. Okay, so let's look at the key differences. So the key differences, okay, of nature and of use. So the vector calculus I, j, and k are unit vectors representing directions in 3D space. They're used to describe spatial relationships and operations like the dot product and the cross product. In quaternions, I, j, and k are imaginary units in the algebra of quaternions. They extend complex numbers to higher dimensions and are primarily used to represent rotations in 3D space. Okay, so in vector calculus, the units are orthogonal and follow simple commutative and associative multiplication rules. and are foundational in expressing and manipulating vectors in 3D. In Quaternions, the imaginary units in Quaternions follow non-commutative multiplication rules, and their square is equal to -1. They provide robust framework for representing rotations, okay, and orientations. So rotations and orientations, but mostly rotations in 3D space. Okay, so that is the main point I want to make here is that the I, J, and K that describe the unit vectors in 3D space are not the same as the I, J, and K in the imaginary units of the quaternion. Okay, so then I asked it the following question. I said, I find the use of the labels I, J, and K very confusing. In terms of teaching, wouldn't it be better to use different letters or labels so we can distinguish between I, J, and K the vector and I, J, and K the quaternion? And it says, so ChatGPT said, you raise an excellent point. The dual use of I, J, and K in both vector calculus and quaternion algebra can indeed be confusing, especially for those new to these concepts, which is probably most of you. Using different labels or notation could help in clearly distinguishing between these two contexts. And here's a way we could do this, okay? Distinguishing notations, vectors in Cartesian coordinate systems. So the current notation is I, J, and K. So they are suggesting the notation E sub x, E sub y, E sub z, or U sub x, U sub y, and U sub z for the units, for the vectors, for the unit vectors, okay? And so E could stand for element or unit in the x, y, z directions respectively. The U sub x, U sub y, U sub z notation, so the U could be used to denote the unit vectors in respective directions. Okay, so I like that. That's all right. And then it gives an example. And then it says in the quaternion notation, so the current notation is I, J, K, as we saw. And so they're suggesting using Q sub I, Q sub J, and Q sub K, or capital I, capital J, capital K, which are both good possibilities, okay? So the Q sub I, Q sub J, Q sub K, the Q prefix could signify quaternion, which would be nice. Using the capital letters to differentiate from the lowercase vectors in Cartesian coordinate systems could also be used. But I like the Q. I think I would probably use the U sub x, U sub y, U sub z, and the Q sub I, Q sub j, Q sub k if I were going to rewrite the language. Okay, so the problem is with the language. This ChatGPT agrees with me that using I, J, K for both the vector calculus and the quaternions can lead to some confusion, and that is, I happen to agree with that I think this is the cause for confusion, not just for the newbies to quaternions, but to the people that are writing papers with these expressions in here where they're actually using I, J, and K for the unit vectors in the Cartesian coordinate system, and I, J, and K using even the same font, so there's no way of distinguishing between the two for the quaternion. So this is what I have a problem with. The problem is with the language. The problem is with the language, with the symbolic language of quaternions and unit vectors, which when you're using quaternions to rotate points in a Cartesian coordinate system, we do need the concept of the vector to know what axis we're rotating about, and we do need the concept of the quaternion. So clearly distinguishing between the two would be very helpful and would remove a lot of the confusion and maybe a lot of the arguments that I'm having with people out there who think that these two things are the same, and they're not. So if I were writing this paper, for example, I would be inclined to write this right here, U sub x, to use U sub x u sub y, and u sub z for the 3 unit vectors. And the reason for this is because this is literally the x-axis, this is literally the y-axis, and this is literally the z-axis. So associating this with x, y, z, I think is a better idea in terms of the language. And then I would still use the I, J, and K for the Quaternions because there's just too much language surrounding that, and I would keep that, but I would relabel the I, J, and K. Okay, so that's what I would do if I was writing this paper to clearly distinguish between these two scenarios. This is what the unit Quaternion, so what we know that I, J, and K, at least in this context, in this paper, refers to these three 1x3 matrices, which are the 3 axes. But what do I, J, and K stand for in the Quaternion? And so using the 4x4 matrix version of Quaternions, I can show that, oh, and I also want to talk about the 1 as well. So you've got A times 1 plus B times I plus C times J plus D times K. So we need to know what 1, I, J, and K are. Okay, so 1, I, J, and K, and I put the positive signs in here because there is a concept of a -1, -I, -J, and -K. And so in the 4x4 matrix implementation of Quaternions, which is the most transparent, the least efficient, most transparent implementation of Quaternions. Okay, so it's not always the most efficient way of implementing Quaternions, but it is the most transparent way of trying to understand what Quaternions are. Okay, so +1, the +1 Quaternion matrix has positive ones in the forward diagonal. Okay, so the +1 in Quaternion language are the locations in the matrix that contain the +1, that contain the unit 1. So this is real 1, this is real 1, this is real 1, this is real 1, okay? So the positive I matrix corresponds to locations in the matrix. So in the positive I matrix, okay, so the I in the Quaternion are locations in the matrix. So you've got +1 here, -1 here, -1 here, and +1 here. And this is what I looks like under the hood. Okay, this is, if you could look under the hood of Quaternions, this is what I would look like. Okay, so then +J looks like this. So we've got +1, +1, -1, -1 in these locations in the matrix. And +K has +1, -1, +1, -1 in these locations in the matrix. Okay, so this is what I, J, and K are in the Quaternions. Okay, in the Quaternions. So this algebraic expression, the 1, I, J, and K all correspond to 4x4 matrices. And these 4x4 matrices are technically transformation matrices. Okay, so this is what they're used for. This is what they do. Okay, this is what they do. This is what they're for. This is how they're used in practice. And so this matrix here doesn't do any rotation. So this is the identity matrix. So if you multiply a vector by like a coordinate, a Quaternion coordinate by this matrix here, that coordinate will be unchanged. Okay, if you multiply a coordinate in the 4-dimensional Quaternion space, like I did in the Mandelbrot set in my previous video, okay, this is going to create a counterclockwise rotation. Okay, this is a transformation matrix. It is not a vector. Okay, it is not directly a vector. It is a rotation about a vector. Okay, so let's go back to this one here. So here are the 3 vectors, And these are the vectors that if you want to rotate only about x, then you would use this matrix here. If you only want to rotate about y, then you would use this matrix here. And if you only want to rotate about the z-axis, you would use this matrix here. You would use this identity here. So these are unit quaternions. And the unit quaternions, technically, at least the imaginary component of the unit quaternions, technically correspond to rotations about the x, y, and z axis. So the general form of quaternions, which is the A1 plus BI plus CJ plus DK, can be seen here. And so basically, if you take the real value A and multiply it by the matrix, the 1 matrix, so the 1 matrix is this matrix here. Okay, so if you take A, the scalar A, the real value A, the number A, whatever that is, that can be positive or negative. If you take whatever is inside of A and multiply it by this matrix, then you're going to get this matrix here. So then you're going to end up with A on the forward diagonal. And of course, when you take the real value B here and multiply it by the I matrix, the positive I matrix, you're going to get B's in these locations here, and it's going to be, so let's say if B is positive, then it's going to be positive B, negative B, negative B, positive B. But if B is negative, then a negative times a positive. So if B is negative, negative B times the positive operator is negative. So you end up with, so if B is negative, this is going to be negative, positive, negative, positive. Okay, so just so you don't get the false impression that the A's have to be positive. Here, if A happens to be negative, and this is going to be negative values on this diagonal. I just wanted to clear that up. I thought that might confuse some people. And so then when you take C, the value, whatever is in C, positive or negative, and multiply it by the J matrix, then you end up with C's in these locations, the C location in the J location of the matrix. So I, J, and K are actually locations in a matrix. Okay, they're not vectors in of themselves. They're actually locations in the matrix. And so then when you take D, whatever that value is, and multiply it by the K matrix, you're going to end up with D's in the K locations in the matrix. And again, say if D is negative, then this is going to be negative, positive, negative, positive. So the signs will change if the D is negative. But if the D is positive, you're going to end up with positive D, negative D, positive D, negative D. Okay, so that's how this all works. And then if you want to do A1 plus BI plus CJ plus DK, you'll add this matrix and this matrix and this matrix and this matrix, and you'll end up with this matrix. Okay, so A times the 1 matrix plus B times the I matrix times C times, or plus C times the J matrix plus D times the K matrix gives you this generalized quaternion matrix right here. So in the implementation of the Mandelbrot set using quaternions, I was using the generalized matrix here, which I just showed you how to build up that matrix. So I just showed you how to go from the unit quaternions to using the algebraic expression. So this is how you build up the algebraic expression with the I matrix, 1 matrix, I matrix, J matrix, and the K matrix. And then when you add these matrices together, because they don't overlap, so A is not B, and B is not C, and C is not D in the sense of the location. So A occupies the forward diagonal, D occupies the backward diagonal, B occupies these locations, and C occupies these locations. And when you add them together, you end up with one generalized matrix. And that is the matrix that I used in the generation of the Mandelbrot set using quaternions. But the main point I want to get across in this video, this very important point, is the problem is with the language. The problem is with the symbolic language, with the use of symbols. Okay, algebra tends to be an abstraction. So algebra is an abstraction. Okay, and I believe the 4x4 matrix versions of Quaternions disambiguate. Okay, so they unabstract what the algebra does. Okay, and so the main point I want to make here is the double use of the I, J, and K for both the 3-unit vectors of the Cartesian coordinate system and the use of I, J, and K in Quaternions, which under the hood are in fact rotation matrices. Okay, they are the I, J, and K are 90-degree rotations. I showed you that in several previous videos. Okay, I corresponds to a 90-degree rotation about the x-axis in the YZ plane. J corresponds to a counterclockwise 90-degree rotation about the y-axis in the ZX plane. And K corresponds to a counterclockwise 90 degrees rotation about the z-axis in the XY plane. Okay, so the problem is with the symbolic language. When you, in a computer program, I wouldn't even be able to use the same variable names for the vector as for the Quaternions, because it would just give me a compile error. It would say doubly, if these were variable names, it would say doubly assigned labels, or, you know, it would give me an error message saying that I have multiple references to the same variable name. Okay, and so I think it's a mistake, and I've seen this over and over and over again, where people use the IJK for the unit vectors in the same context as the IJK for the Quaternions, and I think they even mistake themselves. So if you read the rest of this paper, you'll see that they are thinking that IJ and K they model it as a vector itself, and they are implying that it's a vector itself, when in fact the vector is the Q1, Q2, Q3. Okay, and in the generalized Mandelbrot set, let me get it up here. Okay, the vector is in fact A, B, C, and D. So A, B, and C, and D, whatever they are technically a vector in the 4-dimensional volumetric space of the Quaternion Mandelbrot set, as I showed you in the previous video. Okay, so hopefully you get the point of what I'm trying to get at in this video. I think, again, I've seen this time and time again where people seem to be mistaking, in both these papers, they seem to be mistaking I, J, and K the vector with I, J, and K the rotation matrix. So I think the language could be greatly improved if we didn't do this, if we didn't use these same variable names, the same labels for things that are very, very different, that are in different contexts. So the context of vector calculus is not the same as the context of Quaternions, and so we shouldn't be, when we put them into the same context, like is being done in this paper, okay, as this person did in their paper, then if we didn't do that, then there would maybe be less confusion, not just among the new people, the newcomers to this language, but to the people that have been sort of involved in it a long time and that didn't notice that they were making this mistake. Okay, so some people think, and from my conversations of people from my YouTube channel, I know that some people think that the ij and k in Quaternions, that these ij and k corresponds to a vector, and it absolutely does not correspond to a vector by definition of the word vector. Okay, a vector has direction and magnitude. Okay, here the magnitude is 1. the direction. This is the x direction, this is the y direction, this is the z direction, and the I, j, and k in quaternions correspond to maybe clockwise and counterclockwise. So if this is clockwise, then the complex conjugate of this would be counterclockwise, and if this is counterclockwise, then the complex conjugate of this would be clockwise. So in that sense, maybe you can consider that as a direction, but not in the formal definition of a vector, which has a specific direction and a magnitude in the Cartesian coordinate system in this particular definition of the orthonormal basis for the real three-dimensional Cartesian coordinate system. Okay, so hopefully that makes sense. Sorry for the noise in the background. I think there's a motorcycle going by. I can't do anything about that. But anyways, I'm going to leave it at that, and hopefully I made my point to the people that I'm trying to communicate this to, and to everyone else. So thanks, and have a great day.